Greetings, everyone. My name is Muhammad Sofi bin Sharozizi, and today I am accompanied by my teammates Faik Nabi Ashraf and Habibur Rahman. Today, we are going to be presenting our project, which is the experimental influence of throat design and velocity on properties of T-joint welded plate using Simufact welding software. To start off, as you all may know, welding is a fundamental process for joining metal components. In T-joints, the throat design is actually vital for structural strength. Incorrect throat designs can actually lead to joint failure or bending when subjected to pressure. To start off, as you all may know, welding is a fundamental process. Moving along is our objectives and the experimental matrix used for this study. Our first objective is to, of course, investigate how throat shape and welding speed actually influence the overall joint quality. And our next objective is to evaluate the influence of concave, convex, and miter throat designs to determine the optimal parameter configuration. And our final objective is to analyze the effects of varying welding velocities on thermal distribution. Now, if you can see on the screen right now, we are using 12 specimens for the experiment, each having their own sets of parameters, of course. We have three types of throat designs, which is the convex, the concave, and the miter designs, along with four type of velocities ranging from 10 to 16. Now, I'm going to be explaining the settings used for our simulation. The material chosen for this study is the S23 SPM SW2 material, which is chosen from the Simufact welding library to represent the structural steel plates that includes a temperature application range from 0 degrees to 15,000 degrees Celsius. Moving on, the model design for our project uses a T-joint assembly with three primary plates, which also has a configuration of 8 fixed geometries for stability without the use of any clamping. Next, our project uses a multi-robot configuration which utilizes 4 robots for simultaneous welding. Each robot is, of course, assigned with a specific trajectory. Now, for our simulation, the WPS parameters used are stated in the table above. As you guys can see, for the current parameter, we are using a fixed 100 amps for all of our 12 specimens, along with a fixed 12 volts and an efficiency of zero point 0.6. Now, for the welding velocity, we are using a range of 10 to 16. Now, for our heat source model, we are using a value of 3 millimeters for the front length, 5 millimeters for the rear length, with a width of 6 millimeters, depth of 3 millimeters, and the Gaussian parameter is set at 3. Now, for the most important aspect for our study, the throat design. We have three types of throat designs that we are going to be comparing the results to. We have the concave, the convex, and the miter designs. So, as you guys can see from the images below, the triangle parameter for each throat design is different. If you look at the concave, on the triangle parameter on the B side, we have a number 1, and for the convex it's -1, and for the miter we have zero point 0.0 on the triangle parameter.
Thank you, Sophie, for your wonderful explanation. Hi, everyone. My name is Faik Nabi Ashraf bin Fidaus Ilham, and I'm going to continuing about project result, where the result and discussion section present the finding obtained from the 12 simulation test cases conducted in Simufact welding. Without further delay, let's go to the temperature result. We found that the welding velocity is the most important factor in heat control. As you can see from our data, slower velocity of 10 cm per minute lead to a much broader heat disruption across S235 steel plates. Across all the cases, the maximum terminal profile reached approximately 1517.14 Celsius. But when we increase the velocity to 16 cm per minute, the temperature dropped showing that faster robot speed helps localize the heat-affected zone and prevent overheating. Next, let's take a look at our temperature result that shows in this graph. As you can see, there is a very clear trend here. As we increase the welding velocity, the temperature consistently drops across all design. For example, at the slowest speed of 10 cm per minute, the temperature are at their highest, especially the concave design, which is S5, reached a peak of 17.58 Celsius. However, when we speed up the process to 16 cm per minute, the temperature falls to its lowest point, around 24.15 Celsius, which is S12. This confirms that the higher travel speed are essential for controlling heat and preventing S235 steel from absorbing too much terminal energy. Now, looking at the peak temperature within the well zone, which is the value are much higher. As noted at the table, the highest peak record in the entire study was for the convex design at 10 cm per minute, which is S1, reaching 1709.74 Celsius. Meanwhile, the lowest peak was recorded for the mitre design at 16 cm per minute, which is S12, at 1139.61 Celsius. Slower velocity clearly led to a broader and more intense heat disruption, while the mitre design combined within the highest speed proved to be the coolest configuration. As you can see from the graph, the convex design at 10 cm per minute, which is S1, reached the highest peak temperature in the entire study. You might wonder why the convex design consistently record the highest temperature than concave or mitre. The reason why the convex design is highest is due to its geometric volume. The convex profile had outward curving shape, which meant it required a large amount of filler material to form the well bed. This extra mass of metal acts as a terminal heat sink, holding on the heat from the four robots longer than the thinner design. At the slower speed like 10 cm per minute, this effect is even more wonderful, because the heat source stays over the thicker material for a longer duration, allowing the terminal energy to build up to that peak of 1709.74 Celsius. However, we will see in the end, while this design is the hottest, that the same extra material is exactly what makes the strongest and the most resistant to warping. Now, we move to total displacement. Our results show that concave design S5 at low speed had the most warping, reaching 0.80 mm. This happened because the concave shape is thinner and does not have strength to stay straight as it cools down. In contrast, the convex design, which is S4, at high speed performed the best, with almost no movement at only 0.13 nm. You might ask why the convex design is better. It is because the outward shape adds extra metal to the joint. This extra metal act like a strong pillar and hold the plate in the place to prevent them from bending. For real-world welding, we want the lowest displacement possible to ensure the structure stay perfectly aligned and strong. This is the total displacement graph. This is the total displacement graph. This is the total displacement. Finally, we look at equivalent stress, which explain the internal pressure left inside the metal after it cooled down. Our data showed that concave design, which is S5 at 10 cm per minute, recorded the highest stress at 431.64 MPa. This high pressure happened because the thinner concave shape cannot distribute the force effectively, creating tight spots that could lead to cracks. The convex design S4 at 60 cm per minute achieved the lowest stress at only 327.09 MPa. The convex design is the winner here because outward curve allowed the internal force to spread out more evenly. Even though the higher temperature earlier, the extra metal mass helps the joint to relax better during the cooling process. By choosing S4, we ensure that joint has the lowest internal tension, making the T-joint much safer and less likely to fail under the heavy load. This is the equivalent stress graph. As you can see, the highest is S5, which is 431.64 MPa, and the lowest is S4, which is 327.09 MPa.
Assalamualaikum warahmatullahi wabarakatuh. My name is Habib Rahman bin Hassan. So today I'm going to talk about a discussion about our project. So for this slide, we got two thermal analysis. We got two analysis. For the first one is a thermal analysis, and the second one is structural analysis. So for the thermal analysis, there are velocity inversely affect heat footprint, which mean higher travel speed result in a more localized heat effect zone or HAZ. So when you look at the table, there are welding velocity, heat exposure time, HAZ characteristic, and the result distortion. So for the welding velocity, uh, there are two low and high. So for the low, we are 10 cm per minute, and the high is 16 cm per minute. So for the low one, in heat exposure time, it got too long for the weld, and the hazard characteristic are broad and intense, and the result distortion are high, up to 0.80 mm. So there's a high distortion when we're using a low velocity, and for the high one, the heat exposure time are short, and the hazard characteristic are localized, and for the result distortion, low, they are low. So the minimum or maybe 0.13 mm. So there's a big difference in the distortion for the low and high velocity. So for the structural analysis, uh, concave design provides superior resistance to deform compared to convex profiles, and the convex geometries trap more heat, leading to higher such susceptibility to warping. So when we look at the table, there are analysis factor, convex design, and concave design. For the analysis factor, the HIZ, for the convex design, there are boarding and board and the deep penetration. Different to the concave, it only have narrow and localized. So when we look at the mass displacement, they both have a different So the convex design have high wrapping about 80 mm, and the design concave design have a minimal wrapping about 13 mm. So there's a big difference when we have a different weld design. I mean throat design, the concave and the convex. After after discussion, we go through the summary of the result. So all these in the table are the result after the welding. So when you look at the yellow table, that actually a good result, uh, the best result we get, other than white table. It because convex and velocity are 16, so the temperature, the peak temperature, the total displacement, and the qualivalent stress are different for all these uh, welding design and the velocity. We look at the yellow table. For the temperature, we got max for 24 and the minimum are 20. Different, the others are higher than that, not low than that. So the peak temperature, we got not too high, more than 1050. The maximum 1349. And the total displacement quite big different, and the others it's only 13. And the equivalent stress also are different. We got 327.09. So there's a big difference in the others. uh, for the result that we get. uh, then we go to the conclusion. After we look at the uh, summary result, for the conclusion, after the all the parameters through design that we do, case study 4 is potential configure because it's successful balance high speed production with structural safety by using concave design at 16 cm per minute. So this specific setup achieved a record low displacement of only 0.13 mm, which ensure high dis dimensional accuracy, and the operating at 16 cm per minute is 60% faster than traditional speed and increase production output while minimizing the use of filter material. So the study recommend using concave throat design at higher welding velocities to achieve the best possible result for material, cost, and structural integrity. So that's all for us. Thank you.